Hello and welcome back to differential equations. Okay, this is the part 2 of our matrices. I'm not sure if I can change that now. 1 second, part 2. Can I do that? You are live. I hope this change stays because the lecture is the part 2 lecture for 5.1, which is on. Okay, good. Looks like it's saved. All right. So, hello and welcome back to differential equations, section 5.2, matrices and linear systems, part 2. Right. We are going to continue our lecture on literally half of linear algebra in one lesson. And we're defined already a lot of terms, a lot of mathematical concepts like matrix as a rectangular array of numbers, and then we saw the size of the matrix, rows, columns. We talked about the transpose, adding, subtracting, multiplying matrices, and then we also talked about the inverse of the matrix, determinant of the matrix. We talked about a lot of concepts. What else we talked about? Identity matrix and a square matrices. So all of this stuff, right, that leads us to, there was a zero matrix there, a multiplication of matrices, all of that stuff that leads us into having our matrix valued functions, where we can plug functions inside instead of numbers, and then the derivative, which allows us to take our first order linear systems and write the differential equation the way we're used to, except now we have vectors and matrices. So if last time it slipped, didn't make it clear, this is the matrix, and every other value here with the arrow was a vector. Right, so we have the homogeneous system, and the homogeneous system is the one that we looked at in chapter 4. We looked at matrices with those linear systems, if you remember the operator L and so on. We can tie that in as well. And once we solve the matrix, once we solve the solution, the number of solutions will be equal to the number of rows of the linear system. So in a 2 equation case, we'll have x1 and x2. In 7 equation case, we'll have x1 through x7. And we do the superposition of solutions like we did back in chapter 2, when we add all of the possible answers that we get. We add them all together, and we get the solution x of t. This was the way to write the solution in terms of the column vectors. So if we have x1 solution as a vector and x2 solution as a vector, we can multiply those by constants c and get our x1 and x2 solution written out, and check the independence of solutions using Wronskian, just like we always did. So I think that's where we stopped last time, and I did not have time to go through the any of the examples with right, to check the independence. So I will pick it up here. Let's go to the homework page and find an example where we are supposed to verify that solutions are linearly independent. There we go. So problem number 22. This is a 2 by 2 case. So we had that the x prime is equal to 4, -3, 2, -1 times x. Well, these are all vectors. And then we have our x1 solution given as 2 to the t -3, 2 to the t, 2e to the t, -3e to the t, that's the first vector, and then x2 is equal to e to the 2t and -e to the 2t. So that's what we have. Now we can quickly, put these in a Wronskian and check it. But well, that's the focus of the problem. So Wronskian is going to be 2e to the t -3e to the t e to the 2t and -e to the 2t. I just want to make sure one more time that I copy this correctly. So I have e to the 2t and -e to the 2t. Good. Now we remember the way to solve the determinant of the 2x2. See, I used the wrong notation. I was supposed to use these guys, right? That's for the Wronskian. That's the notation for the determinant. So now we just go and multiply diagonals. So that's going to be -2 e to the 3t, t plus 2t is 3t, and then minus and minus will give us a plus 3e to the 3t, and that is going to be e to the 3t, which is different than 0, which means that the solutions are linearly independent. So, yay, right? Solutions are linearly independent. We don't have to do any of the pre-multiply with x or anything like that, right? No repeated solutions. And we can write our solution. See, now is a good time to write x of t as C1 column vector 2e to the t -3e to the t plus C2 e to the 2t -e to the 2t. So that's what the solution would look like in this vector form. But then you can break this into, if you remember from yesterday, this is the column vector. I keep dropping this this arrow, which is really bad. X1, X2, that's the two solutions. X1, X2 are all the x and y, right, of t. So now I can just, for X1, I will be reading the first row, and then for X2, I will be reading the second row. So, if you follow through the colors, it's very simple. And if you have 16 rows, you'll just have 16 colors, right, for 16 lines. So we're going to have our X1 of t solution. You can represent your solution this way, or you can break it apart into individual lines. So 2c1e to the t plus c2e to the 2t, and x2 of t is -3c1e to the t plus, minus c2e to the 2t. Yay! So here's a big or. You can do one or the other there, both solutions. Okay. Need water. All right, so what's next? What if we have initial conditions? If we have initial conditions, we're supposed to, looking for a problem with initial conditions now. All right, so here's the problem 31, which connects to problem 22, which is the problem above. So now initial conditions. x1 of 0 equals 0 and x2 of 0 equals 5. All right, so when you plug in 0 for t in both of these equations, because both t's are zeros, you have to be careful. Sometimes it's 1, sometimes, right, it's 0, so you can be careful. We're going to get 2c1 plus c2 equals to 0 for x1, and negative 3c1 minus c2 is equal to 5. So as you can see, obviously, well, nothing can change, right? It's the same calculation as before. And you are able now to calculate your c1 and c2. Simply add these two equations because c2 cancels. We get negative c1 is equal to 5. So c1 is equal to negative 5. And if c1 is equal to negative 5, then that's 15 minus 5. c2 should be 10. Because negative 5, negative, yes. Okay, good. So now you will have x1 of t to be 2c1. That's negative 10 e to the t. c2 is 10 plus 10 e to the 2t, and x2 of t will be negative 3c1, that's negative 3, negative, it's so positive 15 e to the t, negative 10 e to the 2t. So that will be solution if you had initial conditions imposed, right, on top of just differential equation, right? To get the general solution, you can also find particular solution figuring out these C's. Now, some of you might ask, does this get worse? Well, always, right? Because these were homogeneous systems, right? It's the one that it's equal to 0. But when you have it equal to a forcing function f of t for each line, right? Then you run into the systems that would have the forced response of the yp. So all of this over here is your good old yc. From chapter 3, right? That will be the, well, in this case, xc or whatever. And then we also need the xp, and the xp is calculated through, you know, other methods. So if you can squeeze in undetermined coefficients, sure. But if you can't, you have to work out things. So again, linear algebra will have its answers in that domain as well. So for non-homogeneous systems, we have our equation dx dt is equal to the matrix p of t times x, and now plus f of t. So this term did not exist in the case above. And the solution will be given as x of t is equal to x of c of t plus x of p of t, all of these being those column vectors of solutions. So you can write it out as x of t being c1 x1 plus c2 x2, these are all vectors depending on how many equations you have, plus c3 x3 plus dot 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 cn xn, because we don't know how many equations we are going to have. That's also, right, a function of t, and then plus xp of t. All of these are of t, right, because these are all functions of time. I see the question again. There is a lag between me teaching and you guys asking questions and me then seeing the question. The answer is yes. 31 is the same question as 22. It's just continuation. In the book, they ask you to solve question 22, and then they ask you to use question 22, which is this here, to solve initial conditions to come up with a particular solution that has C1 and C2 calculated. So that answered the question. If the questions 31 and 22 have the same values and connected, the answer is yes. It could have been just one large question. They broke it into two because there were two parts to it. So for non-homogeneous systems here, this is it. So I'm just going to box this, and then I see the question if we can have another example of what we did before, and the answer is of course we can. I just want to find an example which connects with initial conditions as well, so we can try and do all of the mess at the same time. So it seems that problem 35 links to 26. That's already computed. All right, perfect. So let's go with the unity of problems 26 and 35. Because the question looks the same. So come up with a solution for the system and then use initial conditions to calculate the C's. So problem 26 gives us the system of x prime is equal to, and here's the matrix, 3, negative 2, 0, negative 1, 3, negative 2, 0, negative 1, and 3 times the x. They give us the three solutions, x1, and now this is given a little bit different, so we'll discuss how this works. 2, 2, 1. Then they give us solution x2, which is e to the 3t, and that's going to be negative 2, 0, and 1. And then they give us x3, which is e to the 5t, 2, negative 2, and 1. Finally, in problem 35, they give us that x1 of 0 is 0, x2 of 0 is 0, and x3 of 0 is 4. Yeah, the next problem has 10 and 12, so this is, small numbers is better. So this is your problem statement. And they want us to write the solution, check the Wronskian for independence, and then finally figure out what C1, C2, and C3 are, because we have initial conditions. So these two problems together create one, call it exam problem if you want to, right? For exam 3, they create a single problem. So what do I do here? Well, the first thing is to understand what these now solutions mean, because you haven't seen these ones like that yet. Well, our x of t will be C1 e to the t, and then we have 2, 2, 1, plus C2 e to the 3t, negative 2, 0, and 1, plus C3 e to the 5t, 2, negative 2, 1. We can write them, right? We can break them into x1, x2, and x3. So this is already solution, but it's only the general solution because we haven't calculated these c's yet. Now we can also break this into 3 solutions like this. Now again, you go first row, then you go the second row, and then you go third row. Right, so that's the way you read these solutions. You just have to be very careful. So 2c1 e to the t minus 2c2 e to the 3t plus 2c3 e to the 5t, and that's your first row. Then we have 2c1 e to the t. Now this one is 0, so I'm just going to leave a hole there, minus 2c3 e to the 5t. And finally 1 times c1, so c1 e to the t plus c2 e to the 3t plus c3 e to the 5t. This would be the bunch of solutions that you are used to from chapter 3 and chapter 4. So literally what we learned now in chapter 5 is just a new condensed look for the same solution. Instead of listing all of them separately, if you go back to chapter 3 or 4, whenever I did those, to chapter 3, we had a line for x of t, then we had the line for y of t, right? 2 separate lines, which is technically this. This is your x of t, this is your y of t, this is your z of t, if you want to use x, y, and z rather than x1, 2, and 3. So that's the way to get those together. And now the question is, are these linearly independent? So to check the Wronskian, we'll have the determinant. Now it's going to be 3 by 3, so it's going to take some time. But remember what we are doing here. There is a big fat 0 in here, right? So there's that one. We are going to place these in Wronskian, and we're not going to bother with C1 and C2 and C3. We're just using e's with the coefficients. So 2e to the t, and then 2e to the t, and then single e to the t. So those are those. Then we have negative 2 e to the 3t, a 0, and e to the 3t, 2e to the 5t, negative 2e to the 5t, and e to the 5t. And now, I hope you have your notebooks sideways, because we are going to have a very long expression, right? If you know you remember the 3 by 3 determinant, when you pick one, that eliminates a row and a column. So we have 2e to the t, and over here in parentheses we have 0 plus 2e to the 8t, because you still have to solve the 2 by 2 case using the standard 2 by 2 matrix. So that's the first term. When you pick what we call a pivot, right? When you pick one, then you are left with the 4, right, that are not in that row in a column. You're left with the 4 that create 2 by 2 matrix, and you do the determinant of that one. Okay, then we move to the next one, which is this one. That eliminates row and a column, leaves us with the 4. Now, people usually forget that minus sign there, and then you have negative 2e to the 3t. So this minus sign is in the formula. This minus sign is there because it was there. So be very careful about that. And I have 2e to the 6t. You add the exponents. Minus and minus gives me plus 2e to the 6t. Because 1 plus is 6, yes. And finally, the last one is a plus. So first and the last are plus. The one in the middle is the minus. So now we have this. That's going to be plus 2e to the 5t. And inside we have 2e to the 4t. And then I'll put minus 0, but whatever. There we go. All we need to do is to put all of this stuff together. Now, if you carefully look at the exponents, they're all going to be 9t. And because they're all 9t, we don't have to take derivatives here because we can create matrices with multiple. We already have multiple rows. Only when you have a single equation, to answer the question from the chat, when you only have one equation, like let's say you have c1e to the 5t plus c2e to the 3t. If you just have that, then you take the derivatives to make a second row, and then you do, right? So that's the trick for Wronski. All right, cool. So now, and I think I wrote it out somewhere in blue. There it is, right? As you can see, there are no derivatives in this definition here. All right. So now work this mess out. That's 2 times 2 is 4e to the 9t. This is going to be a plus now, and this distributes as 4e to the 9t. Oh, 2 plus 2 is 4 times 2, that's just 8. Right, these two are 4, and then times another 2 is 8. And then a plus another 4 e to the 9t for a total of 16 e to the 9t, different than 0, so independence, yes. Woohoo! So the solutions are independent. And now the next order of business is to use those initial conditions in here to come up with the values for C1, C2, and C3. So we have x1 is 0, so we have 2c1 because e to the 0 is 1, 2c1 minus 2c2 plus 2c3 minus 2c2 plus 2c3 equal to 0. This equation can be divided by, I'm going to show you something else actually. That equation can be divided by 2 and just loses all of the values. I mean all of the 2's. Second equation is 2c1, come on computer, 2c1 plus 0, I think that was minus 2c3 equals 0. I think there was a minus there. Yep. And then C1, C2, C3 equals to 4. C1 plus C2 plus C3 equals to 4. And now you have a 3 by 3 system which you can solve any way you know. I'm going to divide by 2 these equations. That will create a system with smaller numbers. So we have C1 minus C2 plus C3 equals to 0. C1 minus C3 equal to 0. and C1 plus C2 plus C3 equals to 4. And now solve this any way you know. You can add equations, subtract equations. Now we are already missing second one, C2, right, in the second equation. So we're going to add equations 1 and 3. That's going to give us 2C1 plus 2C3, because C2's cancel, equals to 4. And we still have C1 minus C3 equal to 0. Then you divide this equation by 2 to get C1 plus C3 equals to 2. And C1 minus C3 equals to 0. 2C1 equal to 2. C1 equals to 1. If C1 is equal to 1, then C3 also must equal to 1, so they can create a 0. And I just need to calculate now C2. Now looking at this equation here, let's say C2 must be 2 because they all need to add to 4. And now I have these to plug in and have the full solution. So x1 of t was 2c1, so that's 2e. I forgot all of those coefficients. Actually, what I can do is I can just copy and fix the coefficients. Now I'll just go back and forth. So C1 and C3 are 1s. C1 and C3 are 1s. And C2 is 2, so e to the t. That will be minus 4e to the 3t. Minus 4e to the 3t, and plus 2e to the 5t, plus 2e to the 5t. That's the first one. x2 of t, we just have c1. That was a 2c1, right? Yeah, so 2e to the t minus 2e to the 5t. 2e to the t minus 2e to the 5t, and x3. It's just tedious and long, but it is doable. We have c1 plus c. Okay, these are just all whatever the coefficients are. So e to the t plus 2e to the 3t plus e to the 5t. There it is. So a lot of mess in terms of be careful, right? It's really tedious to put all of these things together, but you know it's doable. You just one step at a time, and it would work out. All right, so just making sure that I didn't miss anything, because this section is really long. So we talked about the general solution non-homogeneous, general solution homogeneous. We talked about the Wronskian. We talked about all of the linear algebra prior to this. The verification of answers, obviously you can either do matrix multiplication or you can plug them in. Depends on what you like better. You are allowed, if you know linear algebra, you can use all of the linear algebra notation and tricks that you learn in that class. If you don't know linear algebra and you know only what you have seen in 5.1, that's fine too. So if you have more knowledge than what is displayed in this section, sure, use it. Yeah, but we covered everything that was in 5.1. That's good. So I will have to restart the stream for 5.2. But before I leave, and there is only 12 of you watching right now, which is not enough for the announcement, but whatever, be here, right? The grading of the exam will take way longer than what I thought initially, because of partial credit is there, but partial credit was always there. The issue now is that I don't have a solution for the test. What I have now is every student has different numbers, and some of you have a slightly different function. So technically, it is every student almost has a different exam, because my MATLAB generates numbers, and in some cases generates a function if the exponent doesn't matter on x. So it's some of you might have x, some of you x squared, some of you x cubed. That changes solutions drastically, obviously, on the other end. This will take years I have to find another way different than my MATLAB for a second one, because what usually was 2, 3, 4 hours, depending on how many students take it per exam, where you all have the same exam, or even two different cases that are already solved. I have to, every question that has to be, that doesn't match the answer that the MyMATLAB I have to solve, because this is the first time for this MyMATLAB. There are a lot of bugs and a lot of errors. I noticed some errors in the calculations that the MyMATLAB has as a solution for the circuit problem. So I'm literally going to do 30-something exams, at least 1 or 2 or 3 problems for each student from scratch, and for some more than 5 or 6 problems, so that we can have the partial credit and so on. This will take forever to grade, and I'm keeping my sanity as well, so I'm not grading 24/7, but I will notify you when the grades are up. So please let your friends know. As I said, only 12 out of 38 are watching this, so live. I know some of you will catch up, but later. But if you are freaking out about the grades, you just chill. All right, relax and let me suffer in peace and silence. I'll let you all know as soon as possible. All right, guys. I will restart in about 5 minutes. I'm going to go get the bottle of water, and we're going to start. We're going to talk about Eigenvalue method for homogeneous systems. This is 5.2, and finally we get to see some solutions and some cool stuff. So I will be back in about 5.